Okay, we're going to cover Chapter 2, which is entitled Discovering the Universe for Yourself. And we're going to go pretty quick, but that's okay. You can always stop this and listen to it again. But we're going to go pretty fast through this first part here. Let's begin by sticking fairly close to the book here, and we're talking about patterns in the night sky. This is section 2.1, and here are our goals for learning. They are the questions that are in the textbook, and specifically it says, what does the universe look like from Earth? Why do stars rise and set, and why do the constellations we see depend upon latitude and the time of year? Okay, well, let's address the first question. What does the universe look like from Earth? Well, if you go outside on any particular night, you'll be able to see lots of stars. If you counted them with your unaided eye, you could probably see somewhere around 2,000 stars or so. But you'll also would be able to see the Milky Way. Now, the Milky Way is a band of what appears to your unaided eye as to be clouds. Now, under really dark skies, you can see it easily. Inside the city lights, maybe you can't see it so easily because it's fairly dim. But it's very prominent under dark skies. You should be able to see that. Now, if you examine it with a pair of binoculars, you'll notice that it's not actually clouds, it's actually lots and lots of stars. So an observer at night could see a couple of thousand stars, could see the Milky Way, maybe could see the moon if it's visible that particular night, and maybe you could also see a few planets out there as well. However, they would look like stars to the unaided eye. Alright, so those are the things that you could see in the sky. Now, the sky itself is divided up into various regions. There are 88 of these regions, and these regions are called constellations. Now, there's not a point that you can point to in the sky that is not within a constellation. So the boundaries of the constellations are sort of oddly shaped. They don't look at all like a constellation you might imagine. For example, the Big Dipper looks sort of like a dipper. The constellation Orion looks sort of like, a hunter or a person. Here, you can make it out if you have a good imagination. All right, but the boundary is not so clearly defined as a human figure or a dipper at all. The boundaries were set up in the 1920s, officially established by the IAU, that's the International Astronomical Union, and that's the official governing body that was established by international treaty that is charged with naming things in the sky, and it defined the constellations in the 1920s or so. And there are 88 of those spread throughout the sky. Now, the stars within the constellations are not necessarily close to each other. They can be very far. They just happen to lie along the same line of sight. So stars like Betelgeuse and Sirius and Canis Major may look like they're fairly close together in the same region of the sky, but they can be very, very far apart in distance. So the 88 constellations then completely cover what is called the celestial sphere. Now, the way to imagine the celestial sphere is this. You have the Earth at the center, and then surrounding the Earth is this gigantic sphere with all of the stars on it. Now, a closer inspection of the celestial sphere shows a few important features that we need to name. In this drawing, you can see the Earth is at the center, and you can see there's a black line on the Earth that represents the Earth's equator. The projection of the Earth's equator outward onto the celestial sphere is called the celestial equator. And then if we project the Earth's north pole onto the celestial sphere, it's called the north celestial pole, and the same thing at the south celestial pole. So we've got those three things defined. There is the celestial equator, the north celestial pole, and the south celestial pole. Okay, there is another line, and it's a great big circle around the celestial sphere called the ecliptic. Now, what the ecliptic is, it is the sun's apparent path on the celestial sphere. So say for example you were to go out during the day and you could see the constellation that the sun was in. Now it would be difficult because when the sun's out you can't see the constellations, but let's say you're above the atmosphere, you can see the constellation that the sun is in, and you would see that let's say the sun is in the constellation Cancer. Okay, but let's go out a month later and look at what constellation the sun is in then, and it turns out that the constellation that it's in is Leo. Okay, and then let's go out a month later and it turns out that it's in a different constellation. So the sun appears to move throughout the sky on the celestial sphere. Alright, well, the apparent path that the sun takes throughout the course of a year, if you were to trace out that path, that would form the ecliptic. So you can see the ecliptic is a great big circle there, and it is the sun's apparent path throughout the year on the celestial sphere. Also notice at this stage that there is an angle of 23.5 degrees between the ecliptic and the celestial equator. Okay, now let's deal with the question of, well, what is the Milky Way? We said it's a band of light, and if you look at it carefully, it's actually stars. But where does it come from? What is that thing out there? Well, what it is our galaxy. We are embedded within our galaxy, and when we look outward, we see this band of light that is our galaxy itself. Now, the galaxy that we live in is a spiral-shaped galaxy, and it is very thin. Here is an image that shows sort of a very thin spiral-shaped galaxy. You can see the white part is the central region, and then there's the galactic plane. Well, we live out, 2/3 or a little over halfway from the central region of our galaxy, where all of those arrows intersect. And if you look up or down in this drawing here, you are looking away from the plane of the galaxy. So there's very few stars in that direction. However, if you look in the direction of the little blue arrows here, then you're looking within the plane of the galaxy. And when you look in the plane of the galaxies, you'll see lots of stars, because the Milky Way is composed of 100 to 200 billion stars here. When we look in the plane of the galaxy, we see the Milky Way. That's that band of light that's going across the sky there. And when we look towards the central region, we'll see what will be a big bulge, and also because our galaxy has lots of gas and dust, then we get these dark regions where the gas blocks our view of some of the brighter stars. But let's define our local sky this way. You'll see there's a person standing here, and we have the directions north, south, east, and west drawn. Alright, the big circle that the person is standing on represents their horizon, so they can see a certain distance in every direction. Alright, now imagine a gigantic bowl that has been placed over the top of this person. Okay, that represents the portion of the celestial sphere that they can see. Now, they can't see the whole sphere because some of it is below the horizon, but they can at least see the part that is above the horizon. Alright, now let's define a few features here. If we draw a line from the north all the way up overhead to the south, that forms what is called the meridian, and that is a great big circle that goes from the north across the celestial sphere to the south. Alright, it intersects at the very top the point that is directly overhead the person, and that point is called the zenith. So the zenith is the point directly overhead. Now let's define altitude. The altitude of an object will be an angular measurement from the horizon. So 0 degrees is at the horizon, and then if you go upwards all the way to the tippy-tip top, that is 90 degrees. So the zenith has an altitude of 90 degrees. The horizon has an altitude of 0 degrees. And we will always have angular measurements then in altitude that is between 0 and 90 degrees then. Now we can locate objects in the sky by measuring how big they appear. So we will measure what's called their angular size. Alright, so the moon, if you measure the moon is about half a degree in size. Now, remember, it's 90 degrees from the horizon all the way up to straight overhead, so the moon subtends an angle of half a degree. The distance between the pointer stars and the Big Dipper, that's about 5 degrees. And if you want to measure things with your hand, stretch your arm all the way out at arm's length, make a fist, and that's about 10 degrees. If you spread your fingers from thumb to the tip of your pinky, that's about 20 degrees. And one finger held out at arm's length, that's about 1 degree. Just to review, degrees are measured this way. We have 360 degrees in a circle, but each degree can be divided up into arc minutes. There are 60 arc minutes per degree, and then each minute can be divided up into 60 arc seconds. So there are 60 seconds per minute, there are 60 minutes per degree, and there are 360 degrees per circle. So here's a good question for you. The angular size of your finger at arm's length is about 1 degree. How many arc seconds is that? Think about it for a minute and see if you can figure out the answer. You might want to pause here. But here's the answer. It's going to be 60 times 60, or 3,600. So there are 3,600 arc seconds for 1 degree.